Hello everyone and welcome back to another video. Today we'll be taking a look at another British Informatics Olympiad question, and we'll be taking a look at a question 2 from the 2019 paper. So let's have a quick look at the question first. I'll just scroll up a bit, and I've highlighted the important parts in yellow, and I'll quickly just explain what exactly the question means, since this one's relatively short. Pretty much, I'd like a quick read first, but what the question requires us to program is some sort of program to model the path of an explorer. And this explorer basically moves following a set of instructions, and these instructions are basically left, right, or forward movements, okay? So this basically means that let's say if the explorer moves forward, then that means they go forward one square, and forward in the current direction they're moving. Left means they go left, right means they go right, and they can't go backwards since that wouldn't really make much sense. And we basically just need to model this situation. So now let's have a look at the whiteboard and how exactly we're going to go about doing this. So one key part of the question is that we need to model a situation such that there are three key directions, sorry, which the explorer can move. These are forward, right, and left, okay? However, the key part in our exploration of this problem is that we won't be treating these forward, left, and right positions as being stationary. All of these will be relative to wherever the current direction the explorer is facing in. So for example, for this particular situation, which we have over here in the leftmost cell, forward would basically be up, and then left and right exactly as normal, just the northeast-west directions. However, if we go to this particular situation, this cell would be forward, this would be right, and this would be left. This basically makes the implementation significantly easier, since this is how the forward, left, right commands, which the question requires us, this is how they work. They're all relative to the explorer. So if you're having difficulties with this problem before watching the video, you might have tried to think of everything just in terms of like forward, left, and right, all of these being fixed, but thinking of them relative to the explorer's position makes it significantly easier to actually program. So then if we basically just get a function which outputs which square is forward, left, or right to the explorer's current position, given the direction the explorer is currently facing in, obviously, then that can be the subsequent square which the explorer moves on. So then that's basically the first part of the problem statement sorted. And now the second part is basically dealing with the whole trail situation which we have over here. So if you remember from the question, there's basically a trail, which means that the explorer can't revisit any part of the trail which they've already been through. So we basically need to somehow store whichever coordinates the explorer has already explored. So we store them in some sort of array, and then this is basically the visited array, if you like, but it's basically a store of whatever the trail already is. And then for this particular visited array, if the next coordinates inside the explorer's path, according to the commands, are within the visited array, then we basically know that that next set of coordinates is not valid. Hence, what we do is we basically turn right, because that's what the question requires us to do. Every time we encounter a pair of coordinates, which we've already been through, we turn right 90 degrees, and then we continue doing this until we find a square. We either find a square, or we find that in each of the four positions, there's already an explored place, which basically means that none of the four positions are valid. And now for this one, this basically means that we break out of the program early. So that's pretty much it for the high-level algorithm, and now we'll just quickly go to the code, and hopefully if you didn't understand it already, you will definitely understand it after looking at the code. So pretty much the high-level like the high-level structure of this code is we have a class game, and this basically represents the coordinate system of which the explorer is in. And then we have this main function move. This basically carries out one particular move, and it carries out the move on one particular command. So let's say the command is forward, so it will move the player forward. However, like there are a bit more intricacies since if the cell in front of it is already taken, then this move function will basically, this move function will then return another move function, which is called, and instead of having forward as the command, it's right. So this move function basically takes care of each move. So then our problem just becomes like implementing the move enough times, n times, where n is the number of moves we need to model. And then if we break early, then that will basically be because we can't make a move. So if we can't make a move, then we break early. And then we finally just need to print off the final game position, which the explorer is currently in. And now we also have this function which basically carries out the rotation. So this rotation basically, given a certain orientation, we basically return whatever the orientation is with respect to whichever command has been executed. And now one key way in which we're representing the orientations is basically representing north as 0 and then right as 1, 2, and 3. So northeast, southwest respectively with the first four numbers, 0, 1, 2, 3. This basically makes rotating much easier since if the current orientation is forward, and then if basically the direction is also forward, then we basically just the new orientation will be forward. So then we just return whatever the current orientation is. Now, if the current orientation is left, then we basically just go left 1. So that means we subtract 1 from new orientation. So I didn't have to do the +4 here, but it adds clarity. What we do is we basically just subtract 1. However, since we have to do this mod 4. So this basically means that from up, if we subtract 1, then we go back to 3. So then we do 0 minus 1 plus 4 mod 3. Okay? And these three basically just deal with outputting the new orientation given a certain orientation. And now let's go on to the actual move function. So what this initially does is it appends the current position into the self-dot positions array. And this self-dot position is basically a track of all the coordinates, which are currently on the path, currently on the trail, if you like, since that's the language which the question used. And now we start by appending that particular position to the array. And then if the length of the positions array is greater than self.n, so what this means is if the trail length is greater than whatever the length which the length of the trail is, then we basically just remove the first element. So the new self.positions array is the previous self.positions array, all of that apart from the first element. And then what we do is we basically set this can't move variable to false. So this can't move acts as a flag variable, basically, indicating whether the move has been finished or not. And then if the move has not been finished, after carrying out all possible, after checking each possible direction which the person can move, then we basically return that. And then that means that the game will basically finish early since the player can't make a valid move. But then, aside from that edge scenario, in the normal situation, what we do is we basically, the current direction will be the rotation of the current direction, as well as whatever the current command is. Now, this current command will be forward, left, right, etc. And then what we do is we just assign the x and y variable to whatever the current position is. And then we carry out the new position. The new position is either x minus 1y, x plus 1y, xy plus 1, or xy minus 1, like the four Cartesian corresponding coordinates to left, right, up, and down. And then if the new position is in the current positions, then we basically set can't move to equaling true, since we can't make this move since it's not a valid move. So then our current command basically becomes right, and then since that's what the question asks us to do, since if we find a position which we've already been through, then we rotate right, i.e. we rotate 90 degrees clockwise until we find a position which we haven't already been through. So then, after this is done, then it continues looping through this while loop, again and again, until it finally reaches a case where the new position is not in the current positions. In that case, we basically make the current self-dot position the new position, and this will basically allow the future. This is the updated location of wherever the traveler is, and then we set can't move to equaling false, since the move is basically finished, and then we break. Okay, and now finally, what we do is we basically just need to carry out this command. And another small intricacy which we have over here is the current command. It will basically be the instructions, where I is the range of moves, mod length of instructions. Since we basically need to carry out the instructions n times. So let's say the instructions are FL. So then after we've finished looping through them, after we've done the second instruction, we need to go back to the first one. So then that's where the modulus operator comes in. And then if we can't make a move, then we basically break, and finally we just print off the position. So that's pretty much it for this particular code. Now let's just test our code on the sample test cases. Maybe let's test on this one. Okay, so we basically got 0, 12, minus 12 is the output. And then if we go back to the question, we can see that that is indeed correct. And then if we finally just test on the last test case as well. Oh, I think I accidentally copy-pasted a bit too much. We just need to copy-paste this. Okay. And we basically get 1, 1 from the program, which we can see is indeed correct. So that's pretty much it for this particular code. I really hope you enjoyed watching this video. If you did, please be sure to leave a like and subscribe. Also, if you'd like to check out the code in more detail, feel free to visit my GitHub down in the description below. And if you enjoyed watching this video, thank you very much for watching, and I hope to see you in another video next time. Thanks, bye.